I would like to recall some derivatives of exponential and logarithmic functions. d dx of e to the x is e to the x. d dx of ln of x is 1 over x. And very useful today, d dx of ln of a function fx is f prime x over f of x. Let's practice a little bit the rule how to differentiate ln of a function. Let's differentiate first ln of sine of x. We are going to do a fraction line. We are going to write the function under the fraction line. So we have over sine x. And above the fraction line, we are going to write the derivative of sine of x. In this case, we have this one. And we get cosine x over sine x, which is also cotangent of x. Let's now differentiate ln of x cubed plus 2x. Again, here is a fraction line. Under the fraction line, I'm going to write the function. So it's x cubed plus 2x. And above it, I would like to write the derivative of that. And I get that. In another example, if I have just to differentiate ln of y, and y is some function, then I have to do the fraction line. Under the fraction line, I will write the function, which is just y. And above the fraction line, I will write the derivative of y, which is dy dx or y prime. We also need to know some property of logarithm, so I would like to recall ln of x to the n is n times ln of x. ln of e is 1, and ln of e to the x is x. ln of the product xy is ln of x plus ln of y. ln of x over y is ln of x minus ln of y. Example, let's try to write this in a simplified way using ln's. Everything that is on the top of this fraction is going to be with a plus, and everything in the bottom of this fraction is going to be with a minus. So we are going to have ln of x cubed times y minus ln of z times t to the power of 2. But now I can even do that. And now I can take all the exponents and use the fact that ln of x to the n is n times ln of x to get that. Let's assume that we have to differentiate this function f of x. This is pretty horrible. I mean, obviously, I can use many times product rule and quotient rule, but this is quite messy. The derivative of product or quotient of function is not the product and the quotient of the derivatives of the functions, but derivatives of sum difference of functions is the sum difference of the derivatives of the functions. The question, can I really use that? Well, I just have to apply logarithm, because applying logarithm will turn the product and the quotient to sum and difference. It will also eliminate some exponents. So actually, if I can use something that has to do with logarithm, or what we are going to call logarithmic differentiation soon, then maybe this is not so horrible after all. So let's start with an example which is not so horrible after all. Actually, You know how to do this because this is just the product of three functions, and in order to differentiate this, you just have to apply the product rule twice. But we are going to do it in an even easier way. We are going to use logarithmic differentiation. So what is logarithmic differentiation? Let's see via this example. The first thing that we are doing is we are replacing fx by y. Now we're going to apply ln both sides. And we get that ln of y equals ln of the product of x to the 4 e to the x and cosine x. But here is the whole idea. We are now going to use property of logarithm to simplify that. Here is the big magic. Instead of a product, we are now having a sum of three functions. We can simplify even more. ln of e to the x is just x. After we simplify this function, now we can go and start differentiating. We are differentiating this implicitly because we have here an equation. We are going to differentiate both sides. It's very easy because we already know that if we differentiate ln of y, we get y prime over y. We know also that when we differentiate ln of cosine x, we have to do the fraction line, cosine x under, and above the fraction line we have the derivative of cosine x, which is minus sine x. Now we have to solve for dy dx, which here we just write y prime. And we get that y prime is 4 over x plus 1 plus minus tangent x, all of that times y. But why is this? So if we would like to get an answer that has only x's, we have to get rid of the y by substituting back the function f of x. As you can see, this was actually implicit differentiation, but it was a very easy one. On one side of the equation, we add ln of y. On the other hand, we have just functions of x. The idea of replacing fx by y is to have x and y, because otherwise it's a little bit funny to do implicit differentiation. The idea with applying logarithm both sides and simplifying was to eliminate the product. In this case, we were using y prime for dy dx because these differentiations are very easy. One side is only y and the other is only expression of only x. Let's now differentiate this function using logarithmic differentiation. In step 1, we are going to replace fx by y. And we get that. Now we are going to apply logarithm. We can simplify a lot now. First of all, we will use the power rule for logarithm and we get 5 times ln of this expression. Now we can break this to a sum and a difference. The 2x e to the x is in the numerator, so we're going to have ln of 2x plus ln of e to the x, which is just x, and then we have to subtract ln of tangent x because tangent x is in the denominator of that. Now we just have to differentiate each part. So here is the implicit differentiation. As usual, when we differentiate ln of y implicitly, we get y prime over y. On the other hand, we are just following the rules of differentiating ln of a function, and also here we have to differentiate x, which is just 1. Now we have to multiply everything by y, because we like to find y prime. But we don't want to have y in the answer. So we're going to replace y by fx. And we get that. Now, do you remember this terrible one? It's not going to be so terrible after all. Let's do that. Let's differentiate this horrible function. Step number 1. We're going to replace fx by y. And here is the fun part. We're going to apply logarithm. And let's see what happens. We are getting sum and difference of ln's of some functions. Now we are just going to differentiate each one. Pay attention that this differentiation is really very easy because we are, again, just following the differentiation of ln of a function. Now we're just going to multiply everything by y. And then we're going to replace y by fx.